In module 3, I'll be discussing on small signal amplifier using a common source EMOSFET device. Contains EMOSFET symbol and signal representation. This is a revision to the previous discussion. Small signal modeling, small signal common source drain feedback, EMOSFET configuration. Numericals based on common source drain feedback amplifier. Then we'll discuss on common source voltage divider EMOSFET configuration for small signal amplifier. So these are the symbols. So in PMOS, you can see the current flowing into the source terminal, and in NMOS, current flows into the gate terminal. So for these ideal devices, when you draw a small signal model, it is like this that appears. The gate to source is open source because it has an infinite impedance. That is why it is an open source at here is a current source. Generally the impedance at the gate terminal is in megaohms, so it is very large and is acting as an open circuit. Here between the drain to source there is a current source, that is GMVGS. Voltage between the drain and the source is VGS. The dynamic resistance between these two is RD. GM is the transconductance between the output and the input terminal. So it's a ratio of output current upon the input voltage, which is equal to absolute value of the admittance into a resistance RD. So 1 upon GM is equal to 1 upon the voltage between the gate, the admittance between the gate and the source terminal. So I'm reading the points to what I have discussed. So EMOSFET N channel or a P channel. Symbolically, when we are trying to represent this symbol into a small signal model, so while performing AC analysis, open circuit between the gate to drain channel and current source from drain to source having a magnitude dependent on gate to source voltage, output impedance from drain to source RD, which is usually provided on the specifications sheet as a conductance GOS or an admittance GOS. A device conductance GM is provided on specification sheet as a forward transfer admittance. YFS, we follow a Shockley's relation. A drain current is equal to a constant value into VGS minus VTH whole square, where VGS is a gate to source voltage and K is a dynamic resistance offered by a device at the output terminal. Small signal modeling. We will again revise over here how to draw the circuit. So GM is a transconductance. As I said, it is a ratio of the input current upon the input voltage GM over here. So input current is a drain current, fine. And VGS is the voltage between the gate to source. We can derivate or the transfer equation to determine GM as an operating point. So operating point in the EMOSFET is decided by the transconductance GM. So GM, you take a derivative of the above relation. So it is delta ID upon delta VGS. We write the equation for the current, that is I is equal to I K times VGS minus VTH whole square. So take the derivative of that, which comes out to be 2K into VGS minus VTH. Since VGTS is a constant value, it gives 0 after derivating that. So GM is equal to 2K into VGS minus VGSQ, which is the operating point gate to source voltage, minus VGTS is the threshold voltage. So on this slide, we have to remember two important points, that is the Shockley's relation and the input conductance, input transconductance. So this is what we have to remember, GM. EMOSFET drain feedback configuration. So in this we'll learn how to draw or how to model a given network. So here what is given is a drain feedback configuration. So again here we can see these coupling capacitors are there, C1 and C2. The role of the coupling capacitor is to block the DC signal from the AC signal. So at present CI is going to block input signal VI from VDD. Similarly, an output AC signal will be will not be affected by the voltage DC voltage VDD. So our first objective is to find the input impedance, output impedance, and at the same time we'll be finding out the voltage gain and current gain for this configurations. To revise a small signal model, an ideal first you start drawing from the ideal network. So here your ideal network is a device itself, that is EMOSFET. So corresponding to that you draw the small signal model here. So GM-VGS is open circuit, a current source acts between the drain and a source. Resistance RD is present, which is generally provided by the data sheet. And later on you connect in the AC circuit model, you connect the external components, that is the resistances RD and RF. So RF is available between the drain and the gate terminal, and your resistance RD is available between the drain and the ground terminal. Now we will solve. So at the KVL, apply a KVL at the input node, that is at the gate terminal. So find out the current. II is equal to GM VGS, a voltage drop, plus GM VGS plus V0 upon RD parallel GM. So VGS is equal to VI. So II is going to be, substitute the value of VGS equal to VI in the equation. Collect all the common terms. Fine. So we will find out the output voltage now. Output voltage V0 is equal to the resistive component, that is RD, small rd parallel capital RD, current flowing out of the output terminal is II minus GMVI. In fact, in this case, the current is flowing into the output terminal. So a positive sign comes over here. The direction of the output current is like this. Right? So this is your output current that is flowing. So that's why voltage drop is going to come positive. So V0 is equal to output voltage. You take a parallel combination and take observe the current flow into the node, and accordingly write the relation. Current II, input current II is VI minus V0 upon RF. So take a help of it. It will be helpful in finding out our output impedance. So II is equal to VI minus RD parallel capital RD into II minus GM upon RF. So we are substituting the value of V0. We are not doing anything different. Right? So as I said few seconds back, II and VI will help us to find out the voltage, will help us to find out the input impedance. So input impedance is equal to RF parallel RD upon 1. Now we have to see, since RF is much greater than RD parallel RF, it simplifies our relation. So Zi is equal to RF upon 1 plus GM in bracket RD parallel RF. So this relation we are going to frequently use when we are performing our AC analysis. This relation will be frequently used. So either you have to remember or you have to derive it so that it becomes a practice for you. It is very important because we will be here. Most of the topics that are designed for the syllabus is analytical. Still further, if RD is like greater than 10 times RD, so it is comparable, right? So we can remove it and make it more simpler. So Zi is equal to Rf upon 1 plus Gm Rd. So very important. So your recollection of formula has also become easier. So Zi is equal to Rf upon 1 plus Gm Rd. Now we have to find out the output impedance Z0. So Z0, what are all the things we need to find out? The voltage Z0 is the output voltage and the output current. So for this, your gate to source voltage is 0. So therefore your GM VGS is going to be 0. So GM VGS is a current source. So that's why we have to open circuit. I have drawn the equivalent AC circuit at the output terminal. Alright. So if the input voltage source is 0, we short it, and if the current source is there, we open circuit that. So that is shown here. So Z0 is equal to RD parallel, small rd parallel RF. Again go back, assume the two conditions. RF is much greater than RD parallel RD, and small rd is greater than larger than the capital RD by 10 times. So Z0 is almost is proportional to RD, that is a drain resistance. We are in a position to find out the voltage gain now. So again reform your relations, that is input current II is equal to GM VGS GM VGS plus V0 upon RD parallel capital RD. So we are trying to find out the current at the drain terminal, at the gate terminal. So input voltage VGS is equal to VI, and the current II is equal to VI minus V0 upon RF. So VI minus V0 upon RF is equal to GM VGS plus V0 upon RD parallel RD. So VGS, when VGS is equal to VI, that is the input voltage, and II is equal to VI minus V0 upon RF. So you break down the relation, this one. So VI upon RF minus V0 upon RF is equal to GM VGS plus V0 upon RD parallel, small rd parallel capital RD. Recollect all the voltages, output voltage and input voltage. Output voltage on left hand side of the relation, input voltage on the right side of the relation. Now take the ratio. Again you make assumption over here that 1 upon small rd parallel capital RD plus 1 upon RF is equal to 1 upon RD parallel RF. So we come to the relation of an voltage gain by taking the ratio of this relation V0 upon VI, and assuming that GM is greater than 1 upon RF, GM over here, Gm is greater than 1 upon Rf. So your voltage gain is going to be negative. So it is minus Gm parallel Rf parallel Rd parallel capital Rd. So since your feedback resistance is very greater than the parallel combination of the dynamic resistance and the resistance between the drain and the source, at the same time Rd, the dynamic resistance is greater than the external resistance that we are connecting between the drain and source. So AV is equal to minus Gm Rd. So important thing what we have learned till now, or what is required when you are doing the analysis of the common source drain amplifier, drain bias amplifier, is that the input impedance Zi, output impedance Z0, and the voltage gain. We'll solve some small problem based on this. So here I'll describe this circuit. Here it is having a resistance between a gate terminal and a ground terminal. Then it has a source resistance which is been bypassed by an capacitance Cs. So at higher frequency, capacitance Cs blocks this resistance Rs, or it short circuits. Then the role of C1 and C2 is to remove the DC component accompanying any AC signal. So these are the coupling capacitors. So knowing the value of Rd and Rs and resulting gain using a relatively high level of Gm, VGSQ is fixed at one-fourth of the value of the pinch of voltage. So you are going to analyze this given circuit and find out the AC parameters like input impedance, output impedance, and the voltage gain. So first perform the DC analysis to find out the operating point Q, which is done in these steps. So VGS is equal to, it is already given, since VGSQ is equal to 1/4 of a pinch of voltage. So pinch of voltage should be given over here, which is equal to 4 volts. Okay, so this will give you VGSQ. Find out the drain current based on this. Then find out the input admittance. GM0 is also given 25 microsiemens or mho. So substitute the value and find out the magnitude of the AC voltage gain by taking the relation AV is equal to GM into RD parallel, capital RD parallel small rd. So gain is given to you over here as 8. Your objective is to find out the ratio of the dynamic resistance and the resistance between the drain and source. So it is 2.13 kilo ohms. Ultimately, we are in a position to find out how this Q point is set. Okay, or what are all the components you have to select when you are setting the Q point or the operating point when VGSQ is equal to 1/4 of the pinch of voltage. So RD is equal to 1 upon GOS. So after finding out a small RD, the dynamic resistance, you find out the drain to source resistance RD. Select a suitable value which is closer to this. So it is 2.2 kilo ohms. Further, the level of RS is to be determined. So go to the input side. Find out the voltage drop between gate to source. So it is minus IDRS. At DC level, these capacitors, all capacitors are going to be open circuit. So we are trying to find out the effective value of RS. So RS standard value is 180 ohms. Okay. Here we are just simply finding out as an overall, the RS doesn't play any role for design of this circuit, because it will be shorted by the capacitance CS at higher frequencies. So that completes your problem design. Next biasing circuit is the common source voltage divider configuration. Fine. Follow the same steps as you had been doing till this state. So first try to study the configuration that is given to you. So the configuration given over here is a voltage divider configuration because of these values of the resistances that are connected between the drain to gate and gate to source. After having known this DC configuration, find out the requirements of like the current voltage drops, what is the effect of this DC source on the Q point, and so on. So this completes your DC analysis. When you are drawing an AC analysis, first you start with a ideal network, second step. So ideal network over here is given by a device, that is EMOSFET. So you draw this, which is shown in the square. It will be common almost in all the biasing circuits. So GMVGS RD, a current source in parallel with the resistance RD. So your input impedance, now we are going to find out the input impedance. So when you're finding out input impedance, what is required is the voltage source, input voltage, and the actual resistance between the input terminal. So you take a ratio, or you take a product of these two resistances as they are in parallel, R1, R2. So input impedance is nothing but equal to a combination of parallel combination resistance R1 and R2. Similarly, when you go back, you look into the network, open circuit this current source and see what will be the resistance that will be coming at the output terminal. So since you are providing an open circuit to the current source, your resistance is the dynamic resistance RD parallel the resistance between the drain and source. As this RD parameter is 10 times greater than capital RD, your resistance Z0 is almost equal to the drain resistance. So voltage gain V0 upon Vi, here little efforts you will have to take. That is, you will have to find voltage drop, relation of voltage drop with the relation of the output voltage. with the input voltage and then take the ratio of V0 upon Vi. So try to understand. First, you find out the output voltage of the network, find out the input voltage of the network, find out how V0 and Vi are related, and then take the ratio of V0 upon Vi. Follow the step that the resistance, the dynamic resistance is very high, which is almost 10 times RD. So your voltage gain will be minus GM RD. So what are all the things for this voltage divider bias sync circuit you have done? In input impedance is a parallel combination of R1 and R2. Z0 is almost equal to the drain resistance. Since your dynamic resistance is 10 times your RD, voltage gain AV is minus GM RD.